Okay, so I'm going to be working through both of the examples that we did not get through in class today because of the, I don't know, technology debacle. The first one is going to be working through kind of the definitions of um, all of kind of the new words and theories that we've learned about yield stress, proportional limit, modulus of elasticity. The second problem, which will be in a separate video, is going to put it all together in a system similar to what we're used to looking at. So for this one, at the proportional limit. So what does that mean? That means if I'm looking at a stress strain curve, it's where we are no longer proportional in terms of this elastic behavior where we have a linear relationship between my stress and my strain. It's like where it's where we use that 0.02 offset method where we can come over 0.002 strain. Okay. A quick side note, the question today in class, if I have a stress strain curve and I have kind of two graphs looking, one looks something like that, okay? This is so we can get a very good bird's eye view of our elastic region. The other one is more like this, and then it just kind of goes maybe over, okay? So if you're looking at it, it's two different colors. So you're going to have values of strain, and maybe they're very large up here on the top, okay? And then on the bottom, it's very similar values, except we are like 0.002, 0.003, but you can see it's a different scale. And it's because if we're trying to look at strains that are occurring in the elastic region, because the strains here are so very, very small before yielding takes place, we could never use the purple scale to figure out what those strains were. So we kind of take the elastic region, we change the scaling of our strain. That way we can actually focus in on the elastic region so that if I want to know at this stress what the strain is, I can actually read those numbers. So they're both the same material. It's just this bottom curve is zoomed into the elastic region. And if you look at the scale at the bottom, then it's going to tell you based on the color of the curve which scale you read. Okay, so at the proportional limit, so that's telling us we are still in the elastic region where our equations are valid. The elastic region stress equals E times strain. That's valid. Once we go beyond that, we don't use this equation, okay? So we have a bar, it's 20 millimeter thick by 75 millimeter wide. It elongates under axial loads. Its original length is 1.6. We have Poisson's ratio. Determine the proportional limit, okay? Determine the modulus of elasticity and the change in lateral directions. So the first thing I'm going to do is I'm going to draw some pictures and I'm going to write down the information I have. I know that stress is force over area, and I know we're elongating. I know that stress equals E times strain, and I know that strain is change in length over original length. So I could also say length final minus length initial over length initial. And I can relate my stress and my strain with my modulus of elasticity. Okay. The other thing is I have this bar and it is 20 millimeters thick and 75 millimeters wide. So we can look at it like this. I'm not drawing it to scale, but here's the cross section of my specimen that I'm looking at, and I'm applying a tensile force. Okay, and actually it's 480 kilonewtons. So I know, okay, that's my internal force. That's P. I also know it has an original cross section of 0.02 meters and 0.075 meters. And you need to start working everything in meters and newtons or kilonewtons because of Pascal. So you just be consistent. Okay, I also know that as I pull on this bar, okay, it gets a little bit longer. And it's telling me it's elongating at 6.8 millimeters, so 0.068 meters. Okay, that's my delta. That's this value. I also know that it has an original length of 1.6 meters. So if I know delta and I know initial, I can calculate the strain. Okay, I could also calculate the final length. So my final length would be 1.6 plus 0.068 meters. And I need to recognize this is my longitudinal change because longitudinal is the direction that we're applying the force, and this area, the change in the cross-section area, is going to be my lateral. So in addition to this is longitudinal, I also know that we have negative lateral divided by longitudinal, and this equals 0.32. So you need to get used to kind of just writing down all of your equations. I know P. I actually know my original area, that's given. I know my change in length. I know my original length, so I can actually find strain. I can find stress. If I can find stress and strain, I can find modulus of elasticity. If I know strain, this is longitudinal strain, and I know Poisson's ratio, I can also calculate that lateral strain. If I know lateral strain, I can find my change in dimensions. So it's just a matter of what do I know? Write them out. Stress equals P over A. Stress equals E times strain. Strain is delta over L. What do I know? And start plugging in. So the first thing we need to find is that proportional limit. And we're just going to start with what I know. Stress equals P over A. So I have 480 kilonewtons, and I'm just going to write that as newtons because I'm weird. And I have an original area, which I can see on here is 0.02 meters and 0.075 meters. And I can divide that out and get 320,000 million pascals, which is 320 megapascals. So this is the stress that's occurring. Okay. And that is going to be the stress of my proportional limit, because it's telling me at the proportional limit, this is my load. This is my original area. So this is the stress that is the proportional limit. Okay. Now I need to find the modulus of elasticity. So this was A. Well, I know that stress is E times strain, which tells me that P over A equals E times delta over length initial. And I can rewrite this however I wanted. If I wanted to find delta, delta would be PL over AE. E is going to be PL over A delta. You can just rewrite this equation. I've already figured out my stress, so I have 320 megapascals, and E delta, 0.0068 meters divided by 1.6 meter is my original length. And so I can cross multiply over here. E equals 320 megapascals times 1.6 meters divided by 0.0068 meters. And when I multiply, do my cross multiplication, I'm going to get that my modulus is 75,294 megapascals, which gives me 75.3 gigapascals. And that's E. That's my modulus. Okay, so now I want to find that change in lateral dimensions. So as I get longer, I'm going to just look sideways, as I get longer, and I have this delta of 0.0068 meters, I also then know, looking at my cross section, that my cross section is getting smaller. So I also have, this is strain longitudinal. I am going to have a lateral strain and a lateral strain that's working on the dimensions of my cross section. So I need to find my longitudinal strain because that's how we can relate our lateral strain, our longitudinal strain with Poisson's ratio, which is 0.32. Okay, so strain longitudinal equals change in length over original length, 0.0068 meters over 1.6 meters, and I get 0.004250 meters per meter, or millimeters per millimeter. Okay, it's unitless, but it's for every meter of length, I'm going to have this much change. So we're going to use Poisson's ratio, 0.32 equals negative strain lateral divided by 0.00425. We're just going to do millimeters per millimeter because we're looking at our cross section in millimeters. And I can get that my lateral strain is negative. So cross multiply, pull the negative over, negative 0.001360 millimeters per millimeters. And it makes sense. It's negative means it's getting smaller. So if my length is positive, getting longer, then my cross-sectional area is actually getting smaller, and our math has worked out saying, yes, indeed, it has getting smaller. So what is strain? Strain is change in length over length, which is length final minus length initial over length initial. So if I want to know what is happening to my dimensions, and if I start out at 0.075 meters or 75 millimeters, okay, I'm getting smaller. And the question says, what is the change in lateral dimensions? So I don't really care what the final length is. I just need to know what is this change in my dimensions. So we have strain, negative 0.00136 millimeters per millimeter equals our change in our width divided by our original 75 millimeters. Okay, so if I cross multiply, I'm going to have that change in my width is negative 0.102 millimeters. So that's telling me it went from 75 millimeters, okay? It got smaller by 0.102 millimeters, so just a little bit smaller, okay? So if I wanted to know what that new width was, I know that delta is length final minus length initial. So I could add the initial length to this. It's going to make that initial length a little bit smaller, and I would have my final length. I can also do the same, 0.00136 equals that height. And our original height is 20 millimeters. Okay, so I will again get a negative value as long as I'm doing my math correct.